We'll wait for 2 minutes. Okay, this was the problem what we solved. Okay, a simply supported beam, and on this there was a concentrated force. Okay, at the center of the span, 50 kilonewton. So we calculated the shear force and bending moment in this one. Okay, so here we have the calculations what we had. Okay, so we considered a section, and every time we went for taking algebraic sum of forces to the left side of the section. Okay, so we moved this section by the interval which was given to us, 1 meter interval. Like that, we are able to obtain what are the shear force and bending moment values in the beam over here. Okay, and we have also assigned the signs for the shear force and bending moment. Okay, so when normally you want to calculate the shear force, take a section at any point at a required interval, and then look for what are the forces to the left of that section. Take their algebraic sum. Okay, left side upward force will be taken positive, downward force will be taken as negative. That is the sign convention we are going to adopt over here. So this is the positive sign convention for the shear force. Okay, left side, if the force is upward, it is positive. On the other hand, right side downward force is taken positive. Okay, like that the sign convention was there. Now then further what we did was we also went for calculating the bending moment in the beam. Okay, when we are calculating the bending moment, okay, so what we normally do is the same section will be there. Okay, we are going to take the section at the given intervals on the beam, then we'll look for the forces which are having moment about that section. Okay, so again we'll be taking the forces which are on the left side of the section, and we'll be taking their moment about that section. Okay, and the sign convention here what we adopt is sagging moment. Okay, this type of sagging moment will arise only when there's a clockwise movement on left side and anti-clockwise movement on right side. If this happens, then the bending will be sagging in nature. So this will be considered as positive. Okay, the positive signs for bending moments will be assigned if at all, if such movements exist in that beam. Okay, so if left side, the resulting movement, if it is coming out to be clockwise, we'll take it positive. On the other hand, if it is anti-clockwise, we'll consider that to be negative over there. Okay, so how we are calculated is, so at A, when we place the section, there were no forces to the left side of the section. So the moment value what we come across will be 0 here. Okay, so after that we brought that section to a distance of 1 meter. Okay, and then what are the forces to the left side of the section? If we look at that, then it is this reaction VA which is coming over here. Okay, so from that what we have is the 25 kilonewton reaction that multiplied by this distance 1 meter. Okay, so it gives us the bending moment as 25 kilonewton meter. Sine what we are having here, this is producing a clockwise moment about the section. At this point, the moment due to this 25 kilonewton force is clockwise, so positive. Next, we'll move by 1 more meter, then we'll come to this point C over here, directly under this concentrated load. At this point, what are the forces to the left of the section? Again, only this 25 kilonewton force. What is the moment of this force about this point C? 25 into 2 meter. Okay, so that is 50 kilonewton meter. Sine, it is having a clockwise movement about point C, where our section is there right now. So positive sign. Then further, if I move to 3 meter distance from me, now 25 into 3, okay, and 50 into 1 meter. Okay? That is what the this one distance is, or the moment is. Okay, so that is the moment what we have due to when our section is at a distance of 3 meter from point A. So 25 into 3, 75. It is having clockwise movement, so we'll assign a positive sign for that. 50 into 1 meter. Now this force is producing an anti-clockwise movement about this point. So that will be taken as negative. So totally, what is the moment at this point? Okay, it is 25 kilonewton meter. Okay, so that is coming out to be positive 25 kilonewton meter. Okay, now again further, but when I come to this support B, at this point, what is the bending moment? It will be this 25 into 4 minus 50 into 2, which comes out to be 0 here. Okay, so this is how we got these values over here. Okay, now question is about plotting this variation. We are studying the variation of bending moment and shear force along the length of the beam. So for that, we have two diagrams. One is shear force diagram and other is the bending moment diagram. We call them as SFD and BMD. Okay, so these are the two diagrams which will represent the variation of shear force and the bending moment along the span of the beam or along the length of the beam. Okay, so shear force diagram is representation of the variation of shear force along the length of the beam, and bending moment diagram is the representation of variation in bending moment along the length of the beam over here. Okay, so for this beam, for which we have calculated the shear force and bending moment at different distances, these are listed here as per our calculation. These are the values what we are getting. Okay, I hope the screen you are able to view what I have shared. It is visible. No problem with that screen and audio. Just give me confirmation.
Visible.
Okay. So this was our section. We placed this section at different intervals: 0 meter, 1 meter, 2 meter, 3 meter, 4 meter. Okay, and at those points we have determined the value of shear force and bending moment here. Okay, so they have been listed here. At 2 meters, I have taken two sections because there is a sudden variation in the shear force. At 2 meter, when we are to the left side of this point C, there is a positive shear force of 25 kilonewton. When I move to the right side of the point C, it is suddenly changing to minus 25 here. Okay, so that is there. So this is all as per the calculation what we have done. The same bending moment calculation at A, it was 0. 1 meter distance, the bending moment we are getting as 25 positive, and at a distance of 2 meter, 50 positive. 3 meter, again 50 positive, and at 4 meter distance, 0. It is coming out to be 0. Now this has to be plotted. Okay, that is what we require here. So it will give us a variation, represent a variation in the bending moment and shear force. Okay, so for that, what we'll do here, first I will show you the shear force, how to plot this shear force over here. Okay, for that, we'll take the beam. Okay, just a line which will be representing the beam over here. Okay, so on this, now what I'll do is I have to plot these values. Just a minute. Okay, so this is my beam, 4 meter span, right? Now, what I'm going to do is I'm going to take these values of bending moment and shear force here. Okay, and I'll be plotting on this. First will be the shear force diagram. What I'm plotting here is shear force diagram. So first at point A, what is the shear force? Okay, it was 0. Okay, when we place the section to the left of A. Okay, when we place to the it to the just to the right of A, suddenly it increased to 25. So from at point A itself, it is increasing from 0 to 25 over here. Wait, I'll just be back. Okay, what I require is a line which is representing the beam. Okay, because we are going to plot it on along the span of the beam. So this is the line what I'll take. This will represent my beam, the span. Okay, and from here onwards, what we are going to do is we are going to plot the variation in the shear force. So at point A, it is 0 and my section is just to the left of this point A. Okay, when I place it to the right of this point A, please tell me if a screen is not visible. No? So here it increased to 25 kilonewton. Okay, so it has increased to 25 kilonewton when it is placed to the right of A. Okay, so from 0 it got suddenly increased to 25 at this point A. Now after a distance of 1 meter, what is happening? It is still 25 till I reach this point C. It is remaining constant, it is 25 only. Okay, so up to point C, when my section is to the left of point C, the value of shear force is 25 plus 25. When I cross this point C, what happened over there? It came to minus 25. So suddenly there is a change in the nature of shear force. So it is coming out to be minus 25. So this is positive, which is, so I have plotted it above this beam line. Okay, this is positive shear force. Now, when I cross this concentrated load, what happened? It became minus 25. Okay, magnitude is 25, but it is negative. Now, up to this point B, till I reach point B, it is constant. Okay, so if you look at the values, what is listed over here, minus 25, minus 25. Okay, it is remaining constant. Okay, so at point B, when I cross the reaction, when I cross the support, just to the right of the support, when I move, what is happening is it is reducing to 0 here. Okay, so this is negative. Okay, so this is how the shear force is varying along the length of this beam. Okay, for this particular beam, what we have calculated, this is the variation in the shear force. We call this as the SFD, the shear force diagram. Shear force diagram. Okay, so that is the shear force diagram what we have. So this is how you plot it. You just take the beam, empty beam. Okay, just draw a line which will be representing our beam. Okay, and start plotting from one of the end. So I've taken from this end A. Okay, this is my end A, B, and here this is the point C where concentrated load is applied. We will not show any support or any loading on this line. We'll simply plot the variation of shear force over here. Okay, so at point A, it was 0. When we just moved our section slightly to the right of this support, it became 25. Okay, so from 0 it has increased to 25 at one single point itself, at point A itself. Now when I move up to point C, okay, it is remaining constant, 25, 25. Okay, even at after the distance of 2 meters, when we are to the left of this point C, the value of shear force is plus 25 only. Okay, so that is the value over here, 25 plus 25. Now when I move this section, okay, towards right of C, okay, when it is placed somewhere over here, just to the right of C, okay, so what has happened here? The value of shear force, now it is minus 25. It is becoming minus 25. So I have taken this line below the beam line, okay, below this beam, right? So it is values 25 only, but negative. Now this is remaining constant till I reach this point B, okay? Even at a distance of 3 meter, it is minus 25 only. When I come to point B, okay, when my section is just to the left of this point B, it is still minus 25. The moment I cross this point, okay, this point B, okay, what will happen is it will become 0, from minus 25 to 0. Minus 25 plus this reaction, we will be adding that, so it will reduce to 0. This is the variation, how we plot that. Okay, is that clear? Okay, then let us see how to plot this bending moment in this case. Okay, if you have any difficulty in plotting this, what I explained now, please ask me. I hope you have understood how to plot it, the values, what will be determined. Okay, now what I'll do is I'll go ahead with the plotting of Benevolent diagram. Now what you have to look for is these values, the distance and the values that has to be plotted on this line. So this line is representing our beam, whatever it is, the beam of 4 meter right now, which is the span. Okay, so this is my beam over here. Now what is the value of Benevolent at point A? It is 0. Okay, so it is 0 over here, right? When I move by a distance of 1 meter, it is 25. Okay, so it has increased to 25, right? And at point C, at a distance of 2 meter, it is 50. So from 25, it increased to 50. Okay, and at a distance of 3 meters, so this is actually, how much is this? So this is again 25 here. Okay, if I, this is by mistake, I have written this. Okay, so this should be not 75, it is 25, because it will be 25 into 375 minus 50 into 1, it comes out to be 25 here. So at a distance of 3 meter, the bending moment value, it is coming out to be 25. Okay, and at B, what is happening here? The bending moment is reducing to 0. Okay, now how it is varying? So with the distance, it varies linearly. Every time you want to calculate the bending moment, okay, if you look at this equation, if I write that equation, it is multiplied by this distance x. The variable is x. X is increasing here. Okay, so every time it is multiplied with x, x to the power 1. So it is varying linearly. It may be 25 into some x may be 1 meter or it may be 2 meter. So it is varying linearly. So this is the variation of our bending moment. Okay. So again, here also the variation is linear, and entirely the bending moment is positive, which means the entire beam is in sagging nature. Okay. So for the entire beam, the bending moment nature of bending is sagging. It will be bent downwards under this loading. That is what it indicates. Okay. So variation, how you get the variation, whether it is linear or not, you have to look at the value of x, the power of x, which we are using over here. Okay, 25 into 1 meter, x is 1 meter. When I multiply over here, 25 into 1 meter, 25 into 2 meter, x is varying linearly, 1 meter, 2 meter, like that. Okay, so this variation is linear over here. So this is how the bending moment is varying. entire beam is subjected to sagging moment. Means when you apply this load, this is the nature of bending of the beam. Okay, this is how it will get deflected or bent. It will be bent downwards here. Okay, you don't worry about that bending nature. Just keep in mind it is a sagging. Okay, if at all the Benevolent diagram, all the values, if they are coming out to be positive. Yes, please tell me whether you are understood or no. How many are there following this one? After calculation, what you need to do is you have to plot it. I don't know what is wrong with this. If you are not understood, please ask me again. Shear force, Benevolent. So the values what you have calculated, they should be taken and then you should plot them. Okay. So here we are getting linear variation in the Benevolent. There are cases further we'll see them where it may be not be linear. It may be varying parabolic. It may be parabolic in nature or it may be cubic in nature. Okay, it depends on what type of load will be applied on the beam. Okay, so in case if there is only concentrated load which is present on the beam, then the bending moment variation will be linear. Okay, so this is 25 kilonewton meter and this is also 25 kilonewton meter. Okay, this is point A, point B, and here was the point C over here. Okay, so shear force diagram, plotting the shear force diagram, take the values of shear force along with the distances, the intervals which were given to us. Okay, the calculated values of shear force, start representing them as a ordinate. At point A, it was 0. From 0, it got increased to 25 here itself. Okay, so this is the ordinate what we have. Okay, and after this, at point at a distance of 1 meter, it is again 25. It is remaining constant. There is no increase in the shear force. It is not changing. So at this distance, at a distance of 1 meter, it is constant over here. It is still 25 kilonewtons. Okay. When I come to 2 meters, when I'm just to the left side of this point C, it is still 25. When I cross this 50 kilonewton load, it is coming out to be minus 25. Okay. Then when I move to a distance of 3 meters, it is remaining same, minus 25, constant. Okay, so this is drawn as a horizontal line, constant. Okay, when I come to this point B, okay, it is minus 25. When I cross this point B, it will reduce to 0 over here. Okay, so this is how it varies, the shear force. Same with the what the Benevolent diagram. Okay, so this is the variation in the shear force what we saw here. Okay, the Benevolent variation also will be something like this. Okay, for that what you have to do is you have to consider the distance and the values of bending moments what are being calculated over here. Okay, so here I have taken the distance at 0 meter, that is at point A, bending moment is 0. When I move by 1 meter at this point at a distance of 1 meter from A, what value we have calculated is 25 kilonewton meter. At 2 meters it is 50 kilonewton meter. Okay, and at a distance of 3 meter, there should have been one more distance here, 3 meter. It is 25 kilonewton meter. When I reach point B, it is reducing to 0. Okay, so these ordinates will be connected by a straight line. The variation is linear. Okay, in this case, only concentrated load is present on this beam. So always in such cases, bending moment varies linearly. Because to calculate the moment at any point, we are just multiplying the distance with the load. Okay, so that is why the uh, variation is linear. You'll understand when we look into further problems wherein you come across x to the power something else, you'll understand the difference over there, how it is linear, how it is not it is a parabolic or a cubic. Okay, but here in this case, this is how the bending moment is varying. Okay, and if at all the ordinates in this bending moment diagram, if they are positive, then entire beam is subjected to sagging. Okay, sagging. So that diagram has to be plotted. Once you calculate the values, okay, you need to plot this Benevolent diagram. Okay, that is actually the representation. It gives a clear picture of how the lower this internal forces are varying within the beam. And purpose of plotting this bending moment diagram is to know that variation itself. Okay, so calculate the bending moments, then and the shear force, then we have to go for plotting it. Okay, so with that, let us to take one more problem over here. Just keep watching this. Tell me about your difficulty or doubts. So let me take the simply supported beam itself. Later we'll go to other beams over here. And this is a roller end. Okay, at this end we have the roller being provided. Okay, and in this case, let's say this beam is carrying a uniformly distributed load over here. Okay, the entire beam is carrying a uniformly distributed load of 30 kilo Newton per meter. Okay, so this is A and this is B. Okay, support A and B, and this is of 5 meter span. Okay, 5 meters. So what you have to do is calculate the bending moment and shear force at every 1 meter interval. Also plot these diagrams. We will always be asked to plot these bending moment and shear force diagrams. Okay. So first is what I require is when I start with the solution, the first thing what is needed is the reactions at the supports. Okay. So in this case, what will be the support reactions? So they are to be calculated first. So can you tell me what would be the support reactions? It is a simply supported beam carrying uniformly distributed over its entire span. Okay, so we can say VA and VB, they will be equal, which will be equal to WL by 2. Okay, VA and VB will be equal. Okay, which and the magnitude will be WL by 2. Okay, have you come across this WL by 2 reaction calculation? Do you remember calculation of reaction in a beam? These are upwards, VA, VB. Or even you can go for applying conditions of equilibrium. Say summation Fy, any one you can do, or is equal to 0. This is my first condition of equilibrium. I'll not take summation Fx equal to 0 since there is no horizontal load present here. So what it gives me is Va. Okay, if I draw this free body diagram of the beam, so this is the reaction at the hinged end upwards, at the roller end upwards. Okay, and this is what the load we have. 30 kilonewton per meter, and this is 5 meters, and these are my reactions VA and VB at A and B. Okay, so VA plus VB minus 50. I'm facing some problem with the system. Okay, but still I'll try. Mhm. Right, so here the reactions are VA and VB. So what I have, condition of equilibrium summation Fi equal to 0 gives me VA plus VB. Due to this UDL, the load or the force will be in downward direction. So minus 30, okay, into the total length. Intensity of UDL multiplied by the length of the UDL will give me total load. So this together should come out to 0, or VA plus VB, okay, is equal to 150 kilonewton if I take it on the other side. So this is one equation what we have. Then taking summation of moment, okay, about point A, I'll take about support A is equal to 0. What I have is VB into 5 meters. So VB will have a anti-clockwise moment about point A minus VB into 5, and this due to 30 kilonewton load, it will be 30 into the length of the UDL 5 meters into the resultant of this UDL will be exactly at the center of this length. Okay, UDL is spread over a length of 5 meter. It will be at the middle of that length. So it will be 2.5, and from my point A or from my support A, it will be at a perpendicular distance of 2.5 meter or so, or into 5 by 2. 71. You have raised the hand. You can unmute and ask what is the problem.
So for a hinge support, there are two reactions, right?
Yes, there are two reactions.
Sir,
You have taken VA only.
Yes, I'll tell you. Summation
okay.
Fi I have taken here. Summation of forces in vertical direction is equal to 0. This is the condition of equilibrium what I have applied. Okay. If I apply summation Fx equal to 0, what happens? HA will be there. Okay, you consider. So for this hinge support, HA, horizontal reaction at A is there. What it gives me? HA, is there any horizontal force applied on the beam? Yes, there's no horizontal force which is present on the beam. Ultimately, HA will come out to 0. So there's no horizontal reaction which is developed at this hinge support because there are no horizontal forces which are applied on the beam. Reactions will develop only if at all if there is any force which is there in that direction. Okay. In general, hinge reaction can offer two. Hinge support can offer two reactions. It can offer two reactions. If you apply horizontal load, it will offer a reaction in horizontal direction. If you don't apply, there will not be any reaction in the horizontal direction. Okay. That is the third law of Newton. For every action, there is equal and opposite reaction. There should be action. For reaction to develop, there should be action first. Is that fine?
Yes, sir.
Okay, so this will be how much? VB. So from this, how much will be VB equal to? 75. From if I take it over here, VB value, it tells me that V is also equal to 75. kilonewtons. Okay, these are the values of V and VB. So 75 and 75. Okay, even if you do with this, you'll get the same value. W30 into 5 by 2, 150 by 2. You'll get the VAVB equal to 75 kilonewtons. Okay, so this is what the reactions are there, right? So now I got to know what are the reactions in this beam. So I have the reactions over here, and the load which is applied on the beam is 30 kilonewton meter. Point A, point B, okay, and these are what 75 kilonewton reaction at A and 75 kilonewton reaction at B. Okay, now we'll go ahead and start calculating the shear force at every 1 meter interval. Okay, so we will consider a section XX. Okay, and we are going to place this section over at the required point and we'll calculate the shear force. Every time we'll go for taking the algebraic sum of all the forces to the left of section, to the left side of the section or this side. Okay, so first is shear force. I'll just put it in short, SF, shear force. This is the abbreviation what you can use. Shear force at point A, or you can say at support A also. Okay, at point A. Okay, so what is the value of shear force left of A at left of A? Shear force value is 0, because when I take this section over here to the left side of this support A, there are no forces on the left side of my section. Okay, so it will be 0. To the right of A, you can take it point A. So what happens when I just move the section to the right side of A? What will happen? This shear force will be equal to sum of all the forces to the left side. Okay, so sum of all the forces to the left side of this section. What I did was my section, okay, I have taken it somewhere at this point. Okay, so this is my section. So what are the forces over here? To the left side of this section, only force is this reaction of 75 kilonewtons. So when I add up the forces to the left side of section, it will be 75 kilonewtons plus 75 kilonewton, because left side upward force is acting, left side of the section, and the force what is there is upwards, so 75 kilonewton. So at A we got the shear force value. It was 0 and suddenly it changed to 75 kilonewton. Okay, so we have calculated at A. Now what we'll do is we'll place this section at a distance of 1 meters from this support A. Okay, because at every 1 meter interval I am interested in calculating the shear force value. The interval given to me is at every 1 meters, so at every 1 meter interval. Okay, so now I'll move this section by a distance of 1 meters. Now what will happen to the shear force? At a distance of 1 meters, so that is from A. Because I started with A as my starting point, I'll be referring to A only. With reference to A only, I'll be calculating every time. Okay, so what will happen here? What are the forces to the left side of this section? What are the forces that are there? One is this 75 kilonewton reaction. Okay, so I'll take that. This is the calculation here. So 75, left side upward force positive, and there is a UDL spread on this 1 meter length. Okay, of intensity 30 kilonewtons, 30 kilonewton per meter. Okay, so when it is spread on a distance of 1 meter, total UDL will be 30 multiplied by the length of the UDL into 1 meter. To the left of my section, there is a UDL spread for a distance of 1 meter. So what will be this total load? It's the intensity multiplied by this distance. Okay, So that will be give me the total load. So 75 minus 30 into 1 meter. Why minus? This UDL is acting in a downward direction. Okay, it is acting in downward direction. And left side, downward force. Okay, the sign convention says if the force on the left of the section, if it is downwards, then it will be so this is our sign convention what we have. I'll draw it over here. This is positive, okay, shear force, and on the other hand, if the forces are having a direction something like this, then we will take it as negative shear force. So left side, the 75 kilonewton was upwards, it was considered positive, and at the same time, this 30 kilonewton UDL, it was having a load in downward direction. So left side, if the force direction is downwards, it is taken negative. So what is the summation over here? Algebraic sum, it will give me 75 minus 30. So it will come out to be 45 kilonewton now at a distance of 1 meter from A. The shear force value is 45 kilonewton. Okay. Then what we have to do is what should be the next section? So I'll move this section by 1 more meter. Okay. So now what is happening here? It is 2 meters. My section is at a distance of 2 meter from the point A now. Okay. So here it is 2 meter now. So at this point, what is the shear force value? Okay. Let's calculate that here. 2 meters from A. 2 meter from A. So for 2 meters, so I'll take it as at 2 meters from A. So here it will be again, if I look at that, when it is at a distance of 2 meters, this reaction will be there on the left side. In addition, the UDL, the part of UDL, what I'll be coming across will be spread for a distance of 2 meters. Okay, when I place that section over here at a distance of 2 meters, okay, so there what will happen is the UDL will be spread for a length of 2 meters. So what I should do in my calculation is, earlier I took 30 into 1, here it will be 30 into 2 meters. So 75 to the left of the section. Okay, so this is the left of the section over here. Look for all the forces, add them with proper signs. Okay, the sign convention what we follow for shear force over here. So 75, the reaction at support A, minus, since 30 kilonewton load, UDL is acting in downward direction. For that purpose, I'm taking it as negative, minus 30 into what is the distance? It is there for 2 meters now, not 1 meter. Okay, it will be for the length of 2 meter over here. Okay, so that is the shear force. This will give me what is the shear force over here. So what happens now to the value of shear force? Minus 30 into 2 meters. Okay, so this will be 75 minus 60. This will come out to be 15 kilonewtons shear force value. Okay, shear force, the unit will be in terms of kilonewtons. For Benevolent, it will come out to be kilonewton meter, right? At 2 meters it is done. Now we'll move further by 1 more meter. What will happen here? At 3 meters, what is going to changes? From point A. Now again, when my section is at a distance of 3 meters from point A, okay, let me make this as 3 meters. It will be more further here, this section XX, okay. So it will be 75. I look for all the forces to the left of this section over here in this section, okay. So what are the forces over here in this section? So that I'll take, right? And so this part, this entire part you have to consider over here, okay. So in this part to the left of the section, what are the forces which are coming here? This 75 kilonewton load, okay, reaction, so that is acting in upward direction, plus 75. And now this 30 kilonewton UDL with the intensity of 30 kilonewton, it is spread for a distance of 3 meters. So minus, because it will be acting downwards, minus 30 into 3 meters. It is spread for a length of 3 meter now. So this will give me the shear force value at a distance of 3 meters from A. 75 minus 90. What will be the value? 75 minus 90. 15 minus 15. This is minus 15 kilonewtons. Okay. So the sign is changed now. Okay. But we don't know where exactly it is changing the sign. I don't have to take any two sections here because there is no concentrated force here. When it is the case where we don't have any concentrated loads applied on the beam, I don't have to worry about taking to the left and right of that section. Okay, so we can just proceed. Later when we plot, we'll come to know where it was changing the sign. What is the next section? At 4 meters from A. Okay, now this will be 4 meter. Again, I'll take what? All the forces to the left of this section. My section is placed at a distance of 4 meters from A. To the left of the section, what are the forces here? I'm coming across this 75 kilonewton reaction, 75, okay, minus what is the UDL? 30 kilonewton intensity, and now it is covering a length of 4 meters here. So into 4 meters, okay. So this will be 75 minus 120. So what will be that? Minus 45. This will be minus 45 kilonewtons. Okay, 75 minus 120. And at a distance of at 5 meters from A. So what will happen to the shear force value? Again, move this by 1 more meter, that is we'll reach point B. So here what we have is 75 reaction will be coming in picture to the left of the section. If I look, that 75 reaction at support A will come in picture, minus 30 into what is the distance now? It is 5 meter. So it will give me minus 75 kilonewtons. This is the value of shear force when my section is at point A. Still I have not crossed point B at point B, but I have not crossed my this point B. Okay, minus 75. After point B, what will happen? Right of support B. What will happen is, what are the forces when I place my section to the right of the B? Okay, when I bring this section, okay, so to the right side of this B, what I'll have is the forces which will come in picture are VA, this UDL, and also VB. I'll be having VB also here. Okay, so there what I have to do is, so I have to take summation of all these forces now. So 75, I'll write it here, 75, okay, VA, this force, minus, now this entire UDL is coming here. UDL is for a spread for a 5 meter distance, minus 30 intensity of UDL into 5 meters. Again, this VB, it is acting in upward direction, left side upward force, plus plus 75, which will come to 0 over here. The value of shear force will become 0 at this point. Okay, so this is the calculation of shear force when we have uniformly distributed load spread over the beam. Okay, the first example what we saw was you can start giving your attendance in the chat box. In the first example, what we saw was the concentrated load was applied on the beam. Okay, in the second, we have seen for the UDL spread over the entire beam. Both we had were simply supported beams. Okay, try doing this calculation again. Repeat this calculation. Okay, the same beam, 5-meter interval, 30 kilonewton intensity. Calculate the shear force values. Okay, if you have understood the bending moment calculation from previous example, try calculating bending moment also. Tomorrow we'll have the master tutorial in the afternoon 2 to 4. I'll be giving you 4 problems and you'll be solving them live. It is you who have to solve. It will be on compound stresses, second module. Compound stresses, this thin cylinders, what is covered in the second module. For your second IA, the portion will be compound stresses and whatever the third module will cover. Okay, I'll tell you up to what point it will be there in the third module. Tomorrow, the attendance for everyone is compulsory. Okay, so see that you have your papers to solve the problems, calculators, everything ready with you. You'll be given the time and then you will be asked to show those solutions. So see that you will have the proper connectivity, at least for the 2 hours, you should be there. Okay, so we'll finish. If you have given the attendance, you can exit.
Excuse me, sir.
Yes.
Sir, I have changed the branch from EC to civil, sir.
Okay. You give it
Sir,
your
we are also having exams, sir.
you give your earlier yes or only. Don't worry about that. Okay.
Sir, we are also having exams, sir.
Master tutorial is there for everyone.
Okay, sir.
Okay. You are joined when you are joined the classes.
Today, sir.
Today only you are joined.
Yes,
Okay,
sir.
you be present.
Yes.
Okay, you be present for
Okay,
that. And you solve whatever is possible. We'll see later. Okay. I'm here
Okay, okay,
live. You can ask me here only. One of you have put questions for master tutorial. Aniket Rai. Questions I'll provide it tomorrow itself. There only. You have to practice from other this one questions what we have solved in the class. Practice them. Okay, it will be provided there
Okay,
only.
sir.
There and then only you solve it. Okay. Aniket Rai.
Okay, okay.
For you, what is your name? 19 EC74. For you, you try to solve what is there. Later, if you have any difficulty in the second module, we'll revise that. The video lectures are available. I'll put them. You can go through them. Okay.
Okay,
And
sir. Okay.
right. Okay.
Okay. Thank you, sir.
Yes. Questions I'll share it tomorrow only. Okay, based on whatever problems you have solved in the class, on that basis you have to try. Okay, it will not be shared in advance this time. Okay, 4 questions, including this Benevolent and Shear Force also. Yes, we can exit.